Hello, my name is Maverick Madison, and this is Lab 3 for EEE120. First, we have the 4-bit D register with enable. What this does is that it takes in a 4-bit input D and an active high enable and sends it through to a 4-bit mux, which then outputs as the input D in binary. Each of the corresponding bits go to each of the corresponding D values in the flip-flops. Alongside this, we have our clock and our reset that also go into the flip-flops. In the end, our 4-bit output from each Q in the flip-flop gives us our final output of Q, where this output line leads directly into our A input for the 4-bit mux. Now, as an example, I'm going to set enable equal to 1 and our D value equal to some arbitrary number like 4. Now, as soon as I alternate the clock, we should expect our output Q to have that exact same result. However, whenever the enable is off and we change D to another value, we are in storage mode for Q. So no matter what we do with the input D, we will always continue to store 4 in Q until our enable is turned back on. So as we can see, whenever we alternate the clock, it does not change. And whenever we start enabling and clock, we get the value 7. And in spite of it all, we can always click reset to reset the entire schematic back to 0. Here is the timing diagram for the 4-bit D register. As we can see, whenever we have enable on and we choose a value for D, in this case it's 15, as soon as we alternate the clock, we get our output Q as the same value as the value D. But whenever our enable is turned off and we switch our value of D, we will continue to store the previous data value in Q until that enable is turned back on. Next, we have the 4-bit up counter. What the circuit does is it utilizes an incrementer and a 4-bit register to continually store and increment our output values to what we please. As an example, I'm going to set enable equal to 1 and start alternating the clock. As we do this, we can see our output Q is incrementing by 1 every time we alternate. But whenever we set enable equal to 0 and we try to alternate the clock, we're in storage mode. So our output Q will not increment. It will stay as our previous data value until enable is turned back on. And if we were to reset this schematic, it will reset output Q to 0. And if we were to turn enable back on and start alternating the clock, we will see again we are incrementing by 1. We can see that our incrementer always has an active high increment value. So this value remains 1 for the entirety of the schematic, so that is how we're actually able to continue incrementing with ease. Next, we have the 4-bit RAM with 16 4-bit words. This schematic allows for us to properly write user-inputted data into particular addresses so that they can be properly stored. In this program RAM already, we have 2 values in the first 2 addresses for 3 and 5. So what we need to do is write a new data value into an open address in the RAM. To do so, we can choose a value to store in, say, address number 3, which is open. I'm going to choose the data value number 7. And after this, all we need to do is write it and alternate the clock. And we should expect our data out to match our data in. And if we actually look into the program RAM, at address 3, we can see our value of 7. Here we have our Brainless CPU. In this schematic, we have multiple inputs, like a 4-bit data in, 4-bit address bus, invert, arith, pass, load accumulator, accumulator to data bus, reset, clock, write, and read. On top of this, we have an ALU. We have an accumulator, which is a 4-bit register, an accumulator mux, which is a 4-bit mux, a data mux, which is also a 4-bit mux, and our RAM. Additionally, we also have 4-bit outputs, ALU out, accumulate, and data bus. This schematic allows for us as humans to be the actual brains of the microprocessor. So we are manipulating each of the lines in order for us to be able to process our data. So let's just do something simple and find the sum of 2 numbers. And we can do this because our RAM already has some predetermined values 3 and 5 in the address 0 and 1. So first, we need to get the 3 into our accumulator. This value is stored in the first index or address of our RAM. So all we need to do is read it and bring it to our data bus. Since our selector is high in the data mux, we are getting our input B and outputting it to the input A of our accumulator mux. And since the selector of the accumulator mux is 0, we are outputting the input value A, which will then be our data bus value of 3 at index or address 0. And this output aligns with the wires of our data in for our RAM, as well as our A input for the ALU. After we get this address data value into our data bus, we need to pass and load this value into our accumulator. And while doing this, we need to simultaneously alternate the clock. So if we pass and load it to the accumulator, we see that our ALU out has an output of 3, which is the value that's stored in the first address of our RAM. And if we clock it, we now have that value of 3 in our accumulator output. Now we are ready to start adding our second value to the first value 3. To do this, we just need to increment our address bus by 1, which stores the value 5. As we can see, our ALU output is 5, but our accumulate is still 3. Why is this? This is because the accumulate output is directly linked with the input B of our ALU. So in order to bypass this, we need to perform an ALU function. The ALU function of adding two numbers would simply be having arith being set to 1 with pass being 0 and invert being 0. And as we can see, our ALU output is 3 plus 5, which is 8. And if we clock that, that value is stored in accumulate output. Additionally, we can see that our ALU output has the value 13 or D in hexa. This is because we loaded the value 8 into our accumulator, and basically the ALU out is performing 5 plus 8, which gives us the value of 13. Here is the timing diagram for the Brainless CPU function of adding two numbers together. So as we can see, we are reading the value at address 0, and we are loading and passing it to the accumulator and clocking. So we can see this as the value 3 in the data bus and the value 3 in ALU out, and as soon as we clock, we get that value into our accumulator, which is also the value 3 at address 0. Then when we want to incorporate our second number to add on to that number, we increment the address to 1, and that gives us a value of 5 in our data bus. And this is where we perform the ALU function of adding. So we turn pass off and turn arith back on. And this gives us the value 8 in our ALU out. And then as soon as we clock, the ALU out turns to the 13 because we're adding 5 and 8 together. And our accumulate has the sum of both address values. This is now where I was able to make some additional tests for this Brainless CPU. The first test was to write a data value from data in to an address in the RAM, this being an external write. We need to pick an address where we want to store our data value. Then we pick our data value. I'm going to choose the data value 7. And we want to write that value into memory. So we set write to be 1. In this case, we have our data bus with that data in value. And as soon as we clock, that will write it into memory. Now, in order to see this, we need to turn everything off and set to 0. And we need to read. Now, as we read each of the addresses, as soon as we reach address 3, we should see the data in value of 7 in the data bus. So at address 0, we have that same value 3. At address 1, we should get 5. Address 2, we should get 0. And address 3, we should get 7, which is the case. So this is how we write a data value from our data in to an address in order to write externally to the RAM. Here are my test values for the first test of writing a data value from data in to an address to the RAM externally. Firstly, we always start with resetting, and then we choose our address and our data to be written. Then we write it to memory, set everything to 0, and then we read at address 3 to see if it's actually stored. And then we do nothing for the rest. This is the timing diagram for the first test of writing a data value from data in to an address in the RAM. And as we can see, the values correctly align with my test values that I just went over. For the next test, we had to store a non-zero value from the accumulator to an address in the RAM, and this is known as an internal write. We can accomplish this by doing the following steps. Firstly, we need to set data into an arbitrary value. I'm going to choose the value 4. And we need to pass and load this into the accumulator. So we set our pass input to 1 and our load accumulator input to 1. And don't forget to clock. As we can see, we have our value 4 in data bus, our value 4 in ALU out, and our value 4 in accumulate. We have successfully loaded into the accumulator. Then we need to pick an address in memory that's available to us so that we can store that value in the accumulator. So in this case, I'm going to choose a place in memory at address number 3 to store this value 4. Next, we just want to write to the RAM and send our accumulator value to our data bus. So we can do this by setting write to 1 and accumulate to data bus to 1 and clock. Now that we have done this, we're successfully able to read our data at an address. So to read our address again, we set everything equal to 0, 0, 0, and we want to start reading at every address to see that our value 4 is stored in address number 3. So we read, we have the value 3 at address 0, address 1 is 5, address 2 is 0, and address 3 should give us a value 4. And you can see that in data bus. Here is the test case for test 2 of storing a non-zero value from the accumulator to an address in the RAM. First, we always have to reset. Then we load our value into the accumulator and set data in, pass, and load to our specific values. Then we choose an address in the memory to send this data. Then we continue with our write operation by setting write to 1, and we want to accumulate to our data bus set equal to 1. And after doing so, we can set everything equal to 0 and start iterating through all the addresses to read our value. So in this case, we are reading at the address number 3 to get our value of 4. This is the timing diagram for test 2 of storing a non-zero value from the accumulator to an address in the RAM, also known as an internal write. And as we can see, everything aligns with the test values that I just went over. Our final test was to perform 2 different ALU operations that stored the results in our accumulator, and we can do this in a single simulation. Personally, I decided to test out the AND and the passing of 2's complement operations. So to start with the AND operation, we need to load our value into the accumulator. So we can do this by choosing an arbitrary value. I'm going to choose the value 3. We need to pass it and load it to the accumulator clock. We can see that our data bus has the value 3, ALU add is 3, and we have our output 3 in accumulator. And since our value is in the accumulator, this is the point where we can start our second value so that we can perform the AND of both of them. As we know in the ALU, to perform an AND operation, all the inputs in the ALU need to be off. So I'm going to turn pass off and then pass our next value. I'm going to choose the value 6 and clock. So whenever we AND 3 and 6, 3 is 0, 0, 1, 1, and 6 is 0, 1, 1, 0. So whenever we AND 0, 0, 1, 1 and 0, 1, 1, 0, we get 0, 0, 1, 0, which is also the value 2. So we have our second value stored in data bus, we have the AND value stored in ALU out, and we have the AND value stored in accumulate. So this is our first operation done. Now to perform our second operation, it's actually pretty easy. We want to perform 2's complement and pass it through. So if we remember from the ALU circuit, in order to perform the passing of 2's complement, we need to have invert, arith, and pass all be equal to 1. So here we have our data input of 6, and we want to perform 2's complement on that. So we set invert, arith, and pass equal to 1. This gives us our 2's complement of 10, because 6 is 0, 1, 1, 0. If we perform 1's complement, it's 1, 0, 0, 1, which is 9, and then 2's complement is just adding 1 to that. 9 plus 1, 10. So we can see this value in ALU out, and as long as we clock, we have that value in our accumulate output. These are my test values for the final test case of where we needed to perform 2 different ALU operations that stored the results in the accumulator. So first, we always reset. Then we load our value into the accumulator by giving an arbitrary data input, and then loading it and passing it. Then operation 1 is where we perform the AND operation of our first and loaded second value. And doing this, we turn off pass and then clock. Operation 2, on the other hand, to pass the 2's complement, is where we simply turn invert, arith, and pass to 1, and then clock. This way, we are able to get our second operation into the accumulate output as well. And after this, we do nothing, but our accumulate output will always continue to store our 2's complement. This is the timing diagram for test 3 of performing 2 different ALU operations that store the results in the accumulator. As we can see, the values align with the test values that I just spoke about earlier. But yeah, this has been Lab 3 for EE120. My name is Maverick Madison. Thank you.